morning or good afternoon, ladies and gentlemen. So my name is Aziz Laouadi. I'm a Senior Research Officer at the NRC Construction Research Center based in Ottawa, Ontario, Canada. And today I'm going to present a new index to evaluate overheating and its application to some selected vulnerable buildings. The presentation will include the following points. After a brief introduction of the topic, I will present an overview of metrics related to overheating, followed by a proposed metric and its application to some selected buildings, and finally some concluding remarks taken from this study. Overheating events arising from heat waves have been identified as a serious concern to public health and well-being. They have caused high toll on population in terms of mortality in various places in the world. Global statistics mention that roughly 500,000 people die every year for the past 2 decades. And recently in Canada, the heat dome in British Columbia has resulted in more than 815 excess deaths. Overheating is found or may be found in all types of buildings, namely free running or buildings without air conditioning, mixed mode buildings which combine natural ventilation with air conditioning, and buildings during power outages or HVAC failure during heat waves. Metrics related to overheating. First of all, an overheating event is defined as a thermal event that results in thermal discomfort and heat stress to building occupant. And therefore, evaluation of overheating will need metrics for thermal comfort and metrics for heat stress. Metrics for thermal comfort are needed in order to set comfort thresholds, values for different types of building and occupants, and also to set comfort requirement for sleeping environment. Heat stress metrics are needed to set thermal limits to avoid any heat-related health injury, and these metrics will need proper physiological models of a human body. There are many approaches to evaluate overheating, but in any approach, the first step is to set the time domain, whether it is the period of the heat wave, the entire summer period, or the entire year. And the next step is to evaluate overheating for a fixed space independently of other spaces of the building. And in this case, the day-to-day community effect is not carried over, or to avoid overheating for occupants where all occupied spaces during 24-hour period of time are taken into account so that the cumulative effect from day to day is carried over. And the next step is to evaluate overheating either from the comfort perspective or from the health perspective. From the comfort perspective, an example of that is to use unmet hours, degree hours, thermal autonomy, etc. From the health perspective is basically to use health outcomes in terms of limiting body dehydration, maximum core temperature, maximum heart rate, etc. And the final step is to set limit criteria in order to declare a space or a building overheated or not. Metrics for heat stress. There are over 100 metrics, but the most popular ones are shown in this table. And in our work, we have selected the standard effective temperature, which is also adopted in ASHRAE standard 55. The scale of the standard effective temperature is shown in this figure here. Values between 22 to 26 correspond to thermal neutrality, and values between 26 to 30 degrees correspond to slight sweating or to slightly warm thermal sensation. And in this range, people can adapt to heat to recover thermal comfort by using simple means, for example, changing their clothing, moving from one space to another, or using ventilation fans to induce some cooling effect. And values beyond 30 degrees correspond to full sweating. And if this is combined with a long exposure time, some health effects will emerge. And health effects will emerge when the core temperature is higher than 38 degrees. And they progress from simple heat cramps or heat syncope to heat exhaustion to fatal heat stroke. So in order to avoid any health injury, we need to develop criteria of overheating in this region here, where the core temperature is between 36 to 38 degrees. To calculate the standard effective temperature, we need a proper physiological model of human body. So to this end, in our work, we have developed two simple models, one for an average young adults and one for average older people. And these models have been successfully validated using public measurement data as shown in these figures. We have used these models to generate heat stress levels for older people under typical indoor conditions. We show in these graphs here the core and mean skin temperature of older people versus those of young people. And as you can see here, under warm exposure conditions, the core temperature of older people is higher than the core temperature of young adults. And this is due to delayed sweating and delayed blood vasodilation. This may constitute health risk since people are not sensitive to heat. They feel they are warm or hot, but they don't feel they are warm or hot. So it is health risk. On the other hand, their mean skin temperature is lower than the mean skin temperature of older people. And this is as well may constitute a health risk. For example, using ventilation fan to induce some cooling effect, it may work for young adults, but for older people, it would accumulate dry heat. And as a consequence, the core temperature of older people will increase. So it is important in a practical situation to not use ventilation fan for older people when the indoor temperature is around the skin temperature. Thermal comfort metrics, contrary to heat stress metrics, there are only few metrics, global metrics adopted in international standards. The most popular one is the predicted mean vote index, which is used for air-conditioned buildings. The adaptive thermal comfort used for free running or naturally ventilated buildings. And there is a third index in between called adaptive thermal comfort for mixed mode buildings. All these metrics have limitations, namely they don't cover comfort for older people, comfortable sleeping environment. In our work, we have improved the PMV index and developed a new index called metabolic-based PMV index. This index covers comfort for young and older people and sleeping environment. And the model has been successfully validated using public domain measurement data as shown in this figure. Comparing the new index with the old index, we can tell here around thermal neutrality or thermal comfort zone, MPV between -1 to 1, both indices give roughly the same results. However, for the discomfort range from the warm side or from the cold side, the new index tends to better estimate thermal sensation vote, whereas the old index tends to overestimate thermal discomfort. We have used this new index to generate comfort requirement for older people versus young adults, as shown in this graph here. So older people having lower metabolic rate than young adults, they perceive the indoor condition as cooler. In order to get the same comfort level as young adults, they will need warmer temperature. Same thing happens for a sleeping environment. Older people will need warmer temperature by up to 2 degrees in order to be in comfort under the sleep state. Our proposed methodology for overheating, we adopted the occupant-based approach in which all occupied spaces during daytime and nighttime are taken into account. And the evaluation of overheating is carried over the heat wave time frame. And the limit criteria are based on heat-related health outcomes. Attributes of overheating, there are 3 attributes. One is the duration of overheating events, which is the number of consecutive days for which the cumulative deviation of the hourly values or the standard effective temperature from its threshold value is higher than a minimum value set to 4 degree hour here. And the severity index is counting all this deviation during daytime and nighttime for the entire heat wave period. And the intensity is basically the ratio of severity to intensity. So according to this attributes, we can distinguish three types of event: long event, intense, severe, or combination of them. And each event may result in different health effect. For example, severe event or long event may result in body dehydration, whereas an intense event may result in high core temperature. We need two threshold values for the standard effective temperature to evaluate overheating: one for daytime exposure when people are awake, and one for nighttime exposure when people are sleeping. These threshold values are building and occupant dependent. Some suggested values are listed in this table. Overheating limiting criteria, we use the health outcomes, basically limiting body dehydration to 3% for young adults as set in the ISO standard, and 2% for older people. Rehydration rate was assumed 80% in typical indoor conditions, and the maximum core temperature is set to 37.6 degrees, and this is lower than the 38 degrees which is used in occupational health and safety standards. Criteria for overheating is basically to limit the exposure duration, severity, and intensity, and these will depend on types of buildings and occupant vulnerability to heat. Application to buildings, we have developed 4 archetypes buildings to study overheating using the new index. Namely, these buildings are residential buildings, long-term care buildings, primary schools, senior social housings. Limit criteria for overheating: for residential buildings occupied by young adults, there are only 2 criteria to be satisfied: limiting the duration and limiting the severity of overheating events. For older people, there are 3 criteria to be satisfied: basically the duration, the severity, and the intensity values. For long-term care buildings, there are as well 3 criteria to be satisfied: basically duration, severity, and intensity. So we have used this methodology and applied to long-term care buildings with a new construction to study some ventilation measures, namely nighttime mechanical ventilation in the common spaces like lounges and halls. And we increased the outdoor air flow rate by 5 times the minimum airflow rate required by existing standards. The second strategy is to nighttime ventilation using bedroom exhaust fans. And the third one is using natural ventilation by simply opening windows if the indoor temperature is higher than 28 degrees and higher than the outdoor temperature. Here are some results showing the room temperature during a 4-day heat wave period in July 2010 in Montreal. As you can see here, the reference room without any measure has its peak daytime temperature reaching roughly 41 or 42 degrees. And by using the strategy to ventilate the common spaces or to open windows, natural ventilation by opening windows, the peak temperature can be reduced by up to 7 degrees. It should be noted here, the overheating events will continue after the heat wave for several days. And this is very important. This period of time has to be taken into account in any evaluation of overheating. This is a graph that shows the minimum and the maximum severity index for the entire building. As we can see here, and indeed the nighttime ventilation of the common spaces is the most effective strategy to reduce the risk of overheating, but it is not enough to eliminate the risk. So the entire building is overheated. So in order to limit, to avoid any health problems to building occupant, this new building, new constructed building should have mechanical air conditioning implemented. So to summarize, overheating evaluation will need comfort metrics to accommodate types of building occupants and heat stress metrics to limit any heat-related health injury. The proposed methodology is based on health outcomes, and its limit criteria is basically limiting the exposure duration, the severity and intensity of overheating. Application of the method to long-term care buildings show that nighttime mechanical ventilation of the common spaces or opening windows or patient rooms are the most effective strategies to reduce overheating risk, but they are not enough to eliminate the risk. Therefore, newly constructed buildings will need mechanical cooling. But for those buildings without mechanical cooling, they should be purged by simply opening windows immediately after heat waves in order or to get rid of the heat accumulated during the heat wave period and to avoid any additional effect on building occupants. Well, more details can be found in this document, which can be downloaded from the NRC website. And by this, I conclude my presentation.